Good morning, everyone. My name is Zhichao. I work for US FDA in Winchester, Massachusetts. Thank you for being here today. I would like to present you to the work we are doing at the FDA laboratories, the efforts on using mass spectrometry for analysis of radionuclides in food. I can forward this in. Here we are. The presentations will discuss 5 aspects of using mass spectrometry in radio.
Lynn, it
Yeah.
did not forward.
It
for
didn't
us.
forward?
Yes, it did. I see outline.
Yes, it just did now. Okay.
Okay, I think there's a delay for some reasons.
But not for everyone.
That's okay.
Yeah.
Go ahead.
So, which includes the user's considerations, right? The methodology limitations and alternative solutions, anticipated applications, and the reference material needs. Let me move it. Oh, go backwards. In the US, the risk-based approach is applied for safeguarding food safety, which consider the radiation exposure along with other factors to assess whether there is an unacceptable risk to public health. Such approach is data-driven and requires a broad range of analytical methodologies. To gain the first-hand information quickly and provide sufficient testing capacity, rapid screening method priority for identify the contaminants in food from a large number of samples collected in the aftermath of a nuclear or radiological emergency. It is also important to gain the quantitative and detailed assessment on the radioactive contaminants for making regulatory decisions with confidence. Here is a list of radionuclides of interest and their respective regulatory limits showing in a different concentration unit used in radiometrics and mass spectrometry analysis. To be applicable, the intended purpose, a screening method should be capable of detecting analyzed radionuclide below 1/3 of the regulatory intervention level. And the method should be capable of, this is for the confirmatory method, and need to be have the detectability for analyzed radionuclide below 1/15 of the regulatory level. The radiometric techniques are deeply entrenched in the detection of and also the quantification of radionuclides. They are also well-known actually, limitations and difficulties, which need to be addressed with alternatives. And here are just a few examples. To put some of these issues into a perspective, let's see 3 examples on applying mass spectrometry to close the capability gap left by radiometric techniques. Now, one of the problems in analysis of Am-241 in food by alpha spectrometry is that the counting source preparation and the subsequent radioactivity counting are tedious and time-consuming, which make it difficult for meeting the high demand for food testing follow a large-scale nuclear or radiological emergency. To achieve the high throughput, sample throughput analysis, and use mass spectrometry to enable rapid screening of Am-241 in food can be a sensible alternative. So a method development project was initiated with the 3 objectives in mind. And the first, sensitive enough to detect M-241 at 5 picograms per kilo. Second, applicable for a variety of food. And third, capable of analyzing 30 samples per 48 hours. These slides illustrated the developed method procedures. And to convert the food into solutions, 50 grams of food is ashed, spec'd with M-243 and solubilized with a concentrated nitric acid. And to extract the M-ration from the sample solution, the solution is loaded onto a column packed with DGA resins, and then reconstituted in 0.5 milliliter of 5% nitric acid. To detect the M-ration, M-241 243 ratios is measured using a quadruple ICP-M mesh and coupled with a desolvation unit to increase the detection sensitivity. Food samples representing 5 different food groups analyzed for M-241. And the difference between the measured and the known values are found to be somewhere around plus minus 3%. The method minimum detectable concentration for M-241 is estimated to be 2.1 picograms per kilograms, which met the required detection limit of 5 picograms per kilo. We find out that the 30 samples can be analyzed by 2 analysts within the 48 hours, starting from ashing the sample to printing the result at the end. Another problem in analysis of uranium in food is that the lack of a compelling method and to make a discriminative detection. If a food contains mixed of natural uranium, depleted uranium, or enriched uranium. To close this capability gap, a mass spectrometry method developed project was initiated, and to achieve 3 objectives. The first has to be able to definitively detect the percent of the EU or the DU in food. Second, it has to be capable of quantifying uranium in food. And third, has to be good for a variety of food. Now, here is the procedure for the method. To convert a food into a solution, you can see 10 grams of food is ashed. However, it's split into 2 subsamples. One spec'd with uranium-233 for quantification, and another without the 233 tracer, and is for the enriched or depleted uranium determinations. Now, both samples portion and are solubilized using concentrated nitric acid and hydrofluoric acid and boric acid. To extract the uranium, each sample solutions is loaded onto a column packed with a UT resin and further treated and then reconstituted using 2 milliliter of 5% nitric acid, which is suitable for ICP-M measurement. And to quantify the uranium, we use a quadruple ICP-MS and measure the uranium-235, 238, and 233. To detect the EU and DU, we measure the ratios of 238 and 235. So you can see the uranium concentration in 2 SRMs were determined using the method. And here's the result. You find to be at least for our applications, intended purpose, and it meets our purpose or requirement. By comparing the measured the sample 238 to 35 ratios against the natural ratios, and you can easily tell, if the food contain either enriched or depleted uranium. So for quantifying uranium in food, the difference between the measured value and the known values are somewhere minus 2.6% to 1.6%. For determining uranium ratios in food, the accuracy is found to be between minus 2.1% to 1.56%. It appears that the method can detect the enriched uranium better than depleted uranium. So to improve the DO detection, it needs a sector field ICP-MS, and that provides a flat top peak and higher ion transmissions, and for a precision ratio measurement. We don't see the mass bias too much, it's quite small if you optimize the instrumentation parameters.
Lynn?
Yeah.
I'm sorry, this is Jackie. It's gotten to the point where it's really delayed.
Mhm.
Do you mind stopping sharing, and I'll try to share your slides
Sure.
and see if it'll go a bit faster.
Sure.
Jackie,
like you're
Jackie,
Yeah.
that it's not delayed for some of us.
It's not. Okay, so it's just me. All right, then keep going and I'll re-sign in. Sorry, thank you for saying that. Yeah, it must be me. Okay.
So we're going to go to the slides. What is the numbers? I believe we're going to talk about we're done with this, right? So we are here, I believe. It is well known the fact that the separate quantification of uranium-239 and 240 and the determination of plutonium source term, it cannot be achieved by using the alpha spectrometry because the resolution is not there. So to close this capability gap, and a mass spectrometry method need to be developed. And the objective for the method development are as follows. To develop a mass spectrometry screening method, right? It has to be detect at least 319 picograms per kilogram of food. This is 1/3 of the FDA limit. Secondly, to develop a QICP-MS method for quantifying uranium-239 and 240 separately in different kind of food. And then we prefer to have the isotopic ratio technique and able measure the plutonium-239 and 240 ratios or other way around, and for source term determinations. So the method has to be rapid and high throughput, and so the response to radiological emergency can be done more effectively. Now here's the procedures for the method, and summarize this like this, right? To convert the food into a 30-gram food that has to be solubilized after being ashed and spiked with plutonium-242, and then add the nitric acid and then the hydrogen peroxide. And then when plutonium will go into the solutions, and we extracted plutonium from food matrix with the DGA resins. And we also add sodium nitrite, and so it can take care of the oxidation states for the plutoniums. This is done by the batch extraction rather than the chromatography column, and because it goes to much faster. The loaded resin is collected and rinsed with dilute nitric acid, And the plutonium is stripped off from the resin using a mixture of HCl, hydrofluoric acid, and also with the ammonia iodides for the reduction of the plutonium. And subsequently reconstituted into a very small volume, 1 milliliter, 5% nitric acid. To quantify the plutonium, you can see this number of plutonium isotopes was measured. To increase the sensitivity, the desolvation units has to be in tandem with the ICP-MS to increase the efficiency, reduce the uranium hydrate interference from uranium-238. Here's some of the results, and you can see it's not perfect, but for plutonium-240, we are happy with it. The issue resides on the plutonium-239 because we're still seeing some level of interference from uranium-230 combined with the hydrogen in the samples. And so this part we still need to continue work with and to improve the method. And so these things are still ongoing. So let's say in summary, right, the method can be used for rapid screening of plutonium-239 and 240 in different food. And that's important because we want one method fits as many as type of samples. The detectability is somewhere around the 52 picogram and 10 picogram per kilo, respectively, for two different isotopes. The quantification for 240, well, it can be done accurately. It's still the problem for plutonium-239. In terms of a source term determinations, I think there's still two issues. One is we need to improve the radiochemical separation, right, to minimize the uranium-238 interferences. And we also need to have a sector field ICP-MS, like a high resolution ICP-MS, and to make a better ratio measurement. So despite the method need I say currently, and I think the radiometric technique still remain as a method of choice for a number of reasons. Detection and quantification of a short-lived radionuclides certainly favorable to the radiometric method, and routine rad monitoring, right? Because it's very cheap, and most laboratory possess the equipment. And the larger scale radiological emergency response when surge in testing capacity is expected. The laboratory with a limited budget, and usually they have a lot of radiometric technique in place. But at the same time, a mass spectrometry technique has been the method of choice for other reasons. And for example, the sensitive detection and the quantification of a long-lived radionuclides. Rapid screening when the time sensitive and the high throughput analysis are essential. And high precision and definitive analysis in contamination source investigations. Those things are very useful and critical for the regulators. So I think a mass spec in this regard do have a unique advantages. Now, regard to the future application of a mass spectrometry in radiological food safety, I think that the current development methods intended for a civilian purpose, basically it's a rapid screening and some kind of unique applications. It is our goal to further improve the method, which will elevate the current method into some sort of a more quantitative and confirmative method with recent founded the high resolution ICP-MS our laboratory received. So what is the need for radiological food safety field, right? And as the end users, and I always look at the different reference material for method development and validations. The needs for food matrix certified reference material for mass spectrometry analysis are extensive, which include those representing the follow sample properties, a wide variety of food matrices, right, including monitoring priority or methodological challenging foods, right? So you want to use a standard reference is really relevant to the method that you are working on. Different radionuclides, right, pretend to a different type of a nuclear radiological incidents. You know, we need the relevant radionuclides in the reference material, and so it can be used. Realistic sample size is important, especially the mineral content, because radiochemists do ash food sample down to the ash, and whatever left over is the minerals. So we need to have this kind of chemical matrix to challenge the chemical separations to make sure we can have a decent recovery and we can take care of the interferences. So that's important. Quantifiable radionuclide concentration close to the level of regulatory concern for allowing assessment method accuracy and precision. That's important because many of the reference material out there, when I see it, is very low. It's intended for challenge the laboratory to make an ultra low level measurement. But what we're doing here is we cannot use it for validation method because there is no quantifiable numbers can give us to give some kind of assessment. We can only say, yeah, we see it, or we don't see it, right? That kind of fashion. But for quantifications, it's not really quite useful. Equally important, the radionuclide solution reference material and enable, for example, the mass bias calibrations, right, obviously, and mass spec instrument optimizations, and also assessment of the impact of isobaric and polyatomic interferences are also important for mass spectrometry. So I think this is what I have, and I would thank you to the folks at the FDA, and they has been a very good supporters to the capability of the FDA radiological capability development. So I stop my presentations and hand it over to Jackie. Thank you.
Thank you. Thank you, Lynn. That was excellent. Great highlight of the activities that's happening at the FDA and where you think you're going and what the needs are, particularly with reference materials. Is there any quick questions?
Yeah, this is Richard. I have a quick question. So with regard to the reference materials, it seems that for some of your measurements, you need a fairly large quantity, you know, tens of grams or more. What if a reference material was pre-ashed? Would that be, I mean, I realize it would be skipping a step of your preparation, but it'd be easier to send you 50 grams of pre-ash than, you know, a kilogram or 5 kilograms of something else.
I think this is excellent ideas. I think in terms of the shelf life, right? Because there is no way we can preserve the food long enough, and that's one problem. If you convert it into an ash, it becomes so much stable. It can stay on shelf for a long time. I think that also reduces the sample size to something is easy to handle. I think as all, the sample ashing part of the analysis for food is not something as critical as the rest of part of the analysis. And Lisa was mentioned concerning the volatile radionuclides may get lost during the ashing. That's a concern. That part, this type of reference material may not be able to evaluate. But in terms of making the reference material with a food ash, and do present a very unique opportunities. I think this is something we can explore. I think you can even combine different type of a priority food to make some kind of composite food ash to really representing a variety of food matrices, and that really increase the method development and validation opportunities. Thank you.
So thank you, Linda. That was turn on my video. That's a very interesting notion, and to follow up on it before Guy asks his question, is there, from the FDA, is there a recipe for the type of generic food product you would like to see? For example, if NIST were to develop an ASH reference material certified for a suite of radionuclides, it would be helpful to have the recipe for what you would like to see in that ASH. So that's just something to think about. Jackie, sorry, back to you.
Oh, well, I'm going to throw it over to Guy.
Well, thank you. So Dr. Lin, we already make tons of different food reference materials if you want. I'm going to talk a little bit about them in a minute, but I would not suggest an ashed food thing, but instead a dehydrated food. And then the laboratory has to ash it themselves. And then especially if you're doing plutonium, because, you know, are you going to make the plutonium more insoluble by actually heating it, you know, baking it, whatever, when you're doing the ash? Or are the MIs that are making the reference materials, you know, going to just spike some soluble plutonium on the ash itself, right? Hence, that's why I would say the dehydrated form, it's very stable, shelf stable, if you will, for a very long time. I'll show you some pictures here in a minute when I talk. So maybe you should give me a call.
I'm going to, in the interest of time, there is one more question in the chat and then we'll move on. Let's see, it says, would the high resolution ICP-MS be able to separate the uranium hydride interference on plutonium-239? And how does this compare with, I think triple quad is what the TQ stands for, ICP-MS with oxygen reaction mode? Yeah, to, I guess, basically reacted out the hydride.
So this question is to me or to everyone?
I think it's kind of to everyone, but it makes sense to be brought up to you. But in this case, I think, did you mention that you had used the Aridus or membrane desolvator to reduce the hydride effect? That's what I thought. So the high resolution, I don't think ICP can actually get rid of the hydride. It probably can a little bit, put it off to the side, but the Aridus also helps, correct?
That's correct.
Yeah.
Well, the triple quad do have some unique perspective, you know, because the resolution is so much better than the high res actually. Well, it's kind of counterintuitive in the sense of when you use a high resolution, you actually use a low resolution mode. So what you're really chasing here is the flat top peak to have the precision for the ratio measurement. So you don't have a much resolution per se, right? It's the worst case scenario you can have. But if you swing to the triple quad, your peak is very sharp. It's very hard for you to sit on the top of the peak constantly to make a ratio measurement. So there's two sides of the coin, right? Depending on what you really need. Our approach is rely on the radiochemical separation to take care of the uranium hydride, rather than to let the instrumentation take care of at the end. Right.
There's one more question, and then I kind of like this question because I think it shows the difference between mass spec community and the radiometric community. Is why do you use a uranium-233 as a spike rather than uranium-232?
The 233 has a much longer half-life. 232 is much shorter half-life. And also, traditionally, the 233 is specifically for mass spectrometry measurement with extremely high isotopic purities. And that's why we prefer to have it.
And also for uranium-232, there's a thorium-232 interference, which will pretty much kill you.
Yeah.
Okay, in the interest of time, we're going to move on. Some really great questions. This is wonderful. I think it'll be a great discussion section. Thank you, Lynn. That was wonderful.